Hi guys, welcome to our lecture on the cardiac action potential. This lesson naturally follows from your last lesson on the action potential. And for the skeletal muscle and nerve action potential, we kind of give you that first because it's a nice simple example of, they're both nice simple examples of action potentials. They only involve two channels, voltage-gated sodium channel, voltage-gated potassium channel. And so it makes sense to introduce you to the action potential in those lessons and how propagation works, things like that. But now we're going to talk about a considerably more complex action potential in the cardiac action potential. Now, this is a subset of the channels and transporters that are involved in the cardiac action potential. The first thing that I will say is do not memorize this table. You are only responsible for the channels that I mentioned in the lesson, okay? But nevertheless, we had two channels for skeletal muscle and nerve. Now look at this. We've got 4, 8, 10, 15, 16 channels here, and that's just a subset, okay? So we're talking about an action potential that is considerably more complicated here. And it's worth noting that. I will also note up front that, for instance, the sodium channel in the heart, it acts very similar to the sodium channel in skeletal muscle and nerve, and so do the rectifying potassium channels, delayed rectifying fires, but they are not the same in terms of the genes. They're not encoded by the same genes. They sort of act the same, so you can treat them as being the same physiologically in the terms that we're going to talk about. But when we talk about mutations in genes, you'll find a mutation in the sodium channel in the heart is not necessarily going to affect skeletal muscle or nerve. In fact, probably will not, okay? So it's worth bearing that in mind. The genes are different, okay? All right. So here is the ventricular action potential in all its glory. And when we talk about the action potential, what we're usually talking about is the ventricular action potential. So when we talk about the cardiac action potential, unless we specify otherwise, this is the one that we mean, okay? This is the one everybody means when they talk about it. So we have 4 phases. We have phase 0, which you'll notice right here, our membrane is sitting at rest here at about -80 or so. And I'm a cardiac cell, and I'm hooked up to my brother over here and my sister over here through gap junctions. And when an action potential propagates through my brother, it hits the gap junctions between the cells, between me and my brother, and my membrane depolarizes because his action potential is now propagating to me. My membrane depolarizes, and the first thing that happens is my membrane potential rapidly goes up, rapidly depolarizes, and this is phase 0 of the cardiac action potential, okay? That is followed by phase 1, which is relative to the rapidity at which repolarization takes place, relatively rapid repolarization. From the peak, that's usually about 30 or so, down to about plus 10 millivolts, okay? So that's phase 1, an initial repolarization. That is followed by a plateau phase, phase 2, where the repolarization slows down and the membrane voltage is still going down, but it's very slow. So we have a plateau phase here. It forms almost a flat plateau. And then we have phase 3, which is another repolarization phase that brings us all the way back down to rest, and that is phase 4, down at the resting potential. Okay? So that's a quick round the horn in terms of the phases and what we're talking about when we talk about the cardiac action potential. So now let's look at each phase in detail. So phase 0 is here. Again, that's a rapid upstroke, and again, that takes place. I'm sitting in the membrane, and when an action potential propagates to me, my membrane gets depolarized a little bit because the action potential is propagated across me across from my brother through the gap junctions. My membrane depolarizes a little bit. When my membrane depolarizes, my sodium channels open, okay, and again, these are tissue-specific genes, so they act a lot like skeletal muscle genes, or skeletal muscle channels, but they're not coded by the same genes. And when the voltage goes up a little bit, we get this regenerative reaction that we talked about in the last lesson, in the action potential lesson. And the sodium channels open, that causes sodium influx, rapid influx of sodium ions. That further depolarizes the membrane. That causes more sodium channels to open. That further depolarizes the membrane. We get this very rapid upshoot in the voltage, and that takes place because the sodium influx is very rapid. And the more rapid the influx of positive charge, the more rapid the voltage will go up, because you are making the inside of your cell rapidly more positive. Okay? All right. So we have our sodium channels, and they are carrying this current, which is mediating this rapid upstroke. We also have T-type calcium channels, which are opening here. So T-type calcium channels are calcium channels that activate at relatively low voltages. And when I say relatively low, I mean lower than the L-type calcium channel, which we're going to talk about in a second. So T-type channels have an activation and an inactivation gate, and they activate down here at lower voltages, so they open shortly, really shortly after the sodium channels start to open. You start to get opening of these T-type calcium channels, a little bit of calcium influx. Not really as important in ventricular muscle as it is in the SA node, which we're going to talk about later in the lesson, but nevertheless, they're there and they open, okay? And you should be aware of them. And you should also be aware of the fact that inward rectifier potassium channels are closing down. Closing is a bad term for it. They stop conducting potassium. So what's happening here when you're at rest, this is the current voltage relationship for this channel. And notice what happens. The equilibrium potential for potassium is minus 95. So, you know, at voltages more negative to minus 95, you get an inward current. That is, potassium actually comes into the cell, okay? And beyond minus 95, potassium goes outward, okay? And for this channel, physiologically, the current is always outward because the membrane voltage is always greater than minus 95. Resting potential here is about minus 88. And you'll notice that at about minus 88 or so, you have an outward current here. Potassium is going out of the cell, okay? And so what you find out is that this channel is mostly open at rest. Well, when the voltage increases, look what happens to this channel. The conductance through the channel goes down. The channel is always open, but the amount of potassium that is allowed to go through the channel decreases through the open channel. This is called rectification. So this is called an inward rectifier because it prefers to conduct inward current. And if your cell ever got to a voltage that is more negative than minus 95, you would find out that this channel likes to conduct current in the inward direction. Now, physiologically, that does not happen. You can do it in the laboratory. That's how this data was generated. But physiologically, you never see it. Nevertheless, it's called an inward current because it was discovered in a lab. It's called the inward rectifier because it was discovered in a laboratory. And when it was discovered, it was noted that it prefers to conduct inward current. So, having said that, we conduct outward current, and as the voltage becomes more positive and less negative, this channel conducts less and less potassium. And that is what inward rectifiers do. They prefer inward current, they do not prefer outward current. And so this drops as the voltage becomes less negative. And so you should bear in mind that that's going on during this phase 0 as well. That is, the voltage is going towards 0 and beyond, and as that happens, the current through this channel goes down, okay? All right. We have phase 1, and what's happening during this phase, the sodium channels are inactivated. So very similar to skeletal muscle and nerve, these sodium channels, the voltage goes up, they flip open really quick, and then the inactivation gates are kind of lazy, and they eventually get around to closing at higher voltages, but it takes them a while. And the period between that rapid opening and the very slow closure is the period where sodium is rapidly coming in and your phase 0 shoots up, and now your inactivation gates are starting to close at the higher voltage, and the sodium channels are inactivating during this phase. So we have less inward current, we have less sodium rushing into the cell as this inactivation takes place. And then we also have the opening of the transient outward current channel. This is a potassium channel, okay? And that potassium channel opens at more positive voltages as the membrane depolarizes. So these channels are opening and letting potassium out, just as the sodium channels are inactivating and allowing less sodium to come in. And the net result is a decline in the voltage that you see here in phase 1, okay? These channels do inactivate. They have an inactivation gate, unlike the delayed rectifiers that we're going to talk about in a second, and unlike the delayed rectifier that we talked about in skeletal muscle. Okay, so this actually inactivates as the voltage with time. So we have an inactivation gate that closes as the voltage goes up. So similar to the sodium channel, this has an activation gate that opens. Now it doesn't open as fast as the sodium channel gate does, but it does open quickly enough to mediate this phase 1. And then we have an inactivation gate that is slower, and it that current gradually inactivates as we exit phase 1. Okay, and that's part of the reason why we enter this plateau phase. Although we're going to get that said in a second. So as we enter the plateau phase, this current inactivates. Okay. And then we have L-type calcium channels. These are different than the T-type. They open at a less negative, more positive voltage, but they also act very similar to sodium channels. They have an activation gate that opens rapidly, and they have an inactivation gate that closes more slowly. And in the time between the rapid activation and the slow inactivation, you get a calcium current. So calcium is an inward current that is just beginning to start during this phase, okay? The calcium is just starting to come in, all right? So we have our open calcium channels. They're beginning to open during phase 1, all right? So the activation gate for the calcium channel, relative to the inactivation gate, it's fast, but relative to the sodium channel activation gate, not so fast, because it takes a little while for it to start to open, but it's starting to open during this phase, okay? Phase 2 is our plateau phase. So first thing you'll notice is that the currents during this phase are small relative to phase 0, where you get this huge increase in voltage because you get this massive influx of sodium. That's a really big current. And so the currents during this plateau phase are small relative to that phase and small relative to phase 3, where we're getting this relatively rapid repolarization. So that's one thing to bear in mind. And what that means is that these currents are fairly easy to disrupt. And so it's fairly easy to cause this plateau phase to lengthen or shorten by altering the currents that flow during that phase a little bit. And when you do the long QT program that I wrote, what that centers around is lengthening and shortening that plateau phase. It's very easy to do pathologically because the currents are relatively small and therefore relatively easy to disrupt. Now what's happening during this plateau phase is these small currents are in balance. And because they're in balance, the voltage isn't changing that much. So you have a little bit of inward current going on, and you have a little bit of outward current going on, and the two balance each other out so that the net change in voltage is really small, okay? And the two types of currents are in balance during this phase, and that's why you get this plateau phase. You're not getting a lot of net inward current, and that would cause a depolarization, and you're not getting a lot of net outward current. That would cause a repolarization. So what you're seeing is a balance between the two. So we have the sodium-calcium exchanger that is active during this phase, and it's mediating an inward current because you're allowing 3 sodiums to come in for 1 calcium ion to go out. That's a net of 1 plus charge every time this transporter turns over. So that's mediating an inward current. So your sodium-calcium exchanger and your L-type calcium channels are pulling your voltage up. They're allowing positive charge to come in. okay, during this phase. And you have L-type calcium channels, again, allowing calcium to come in. And that's balanced by your delayed rectifier channels. That's IKS, IKR, and IKUR. IKS, S stands for slow. So as you might expect, these are slow to open. IKR stands for rapid, R stands for rapid. So these open faster than the slow channels. IKUR is ultra rapid. These open faster than the rapid. This is relatively weak in ventricle. It's stronger in atrial myocytes. We'll get to that later in the lesson. These two are fairly strong during this plateau phase. So they're allowing potassium to go out of the cell. So these are outward currents. So we have outward currents in the form of potassium currents balanced by inward currents in the form of sodium-calcium exchange, allowing an extra positive charge to come in, and L-type calcium channels allowing a 2+ charge to come in. So these are in balance, and because they're in balance, we see very little change in voltage, just a very slow repolarization. Phase 3, the first thing that you'll notice is the voltage now is starting to gradually more rapidly decline during phase 3. And because the voltage is declining, your activation gates on the L-type calcium channels are closing. We call that deactivation, okay? And you're also continuing to get inactivation of the L-type calcium channels. As long as this voltage is hanging up, you're getting inactivation of those channels. So you're getting a loss of calcium current toward the end of this plateau phase and at the beginning of phase 3. And because you're getting less inward current, which tends to pull your voltage up, less positive charge coming in, it's easier to repolarize, and that's one reason why phase 3 repolarizes more rapidly than phase 2 does, because these calcium channels are starting to deactivate and inactivate. And then we have our delayed rectifiers, which are really becoming more and more strong as this depolarization continues. So particularly IKS channels continue to open. So what they do is they start to open at the very beginning, and they become gradually more and more open, and they conduct gradually more and more outward current, that is potassium leaving the cell. And as the IKS in particular gets stronger and stronger, you start to bring your voltage back down again because your outward current has become stronger. And so you can think of the plateau phase as being a balance between the inward and outward currents. And at the end, what happens is the outward currents win. The IKS in particular continues to open. Your L-type calcium channels are shutting down. And so the balance goes in favor of the outward currents, which means positive charge leaving, potassium leaving, voltage going down, and your voltage goes down more rapidly because of that. Okay? So we go from a balance between the two to where the outward currents eventually win. Okay? And as you get toward the end of phase 3, look what's happening. Our voltage is coming back down again, and look at our inward rectifiers. The outward current is gradually going up as we get more and more negative. So they are also conducting an outward current, potassium leaving the cell, and so they help get this last bit of repolarization in, and they help bring it down, bring this voltage down relatively rapidly toward rest. Okay, so they kick in toward the end of phase 3 and help. They gradually become more and more powerful, more and more outward current, and you come down to closer to the resting phase. Okay, and then finally you get at rest, and the primary current that's being conducted at rest is the inward rectifier. So you're at about minus 80 to minus 90, somewhere in this range. And you can see you've got a reasonable outward potassium current, and that's the primary current that's flowing during rest. Okay, so this current tends to keep you at the resting potential, and this is the current that has to be overcome if you're going to depolarize the membrane during phase 0 with that rapid influx of sodium. So this current really holds you down at rest. Okay. Okay. That's all I have for this video. Stick around and we'll start with the second video as soon as you're ready.